come. Okay, so let me just give a glimpse what is the confusion matrix and everything. Okay, you understand that very well, and then we'll continue with our new algorithm, right? Let me just give a glimpse. What is the confusion matrix? Simple. Okay, suppose I create a matrix. What happened here? Why it is not? Yeah, fine. I create a matrix here. Okay, on this side of the matrix, I'm representing actual values. Okay, and here I'm representing predicted values. Right now, suppose I have two classes. Okay, take it that way. Take it that way. We have two classes. One is positive class, one is negative class. Okay, so actual here I'm mentioning actual positive, and here I'm mentioning actual negative. Okay, here I'm mentioning predicted positive, and here I'm mentioning predicted negative. Okay, so whatever you will mention here, positive or negative, that will be according to the predicted only. For example, what predicted is saying positive. In complete row, it should be positive. So we mention here positive, positive. What it is saying here, negative. So I will mention negative, negative, as simple as that. But now see everyone. Come here, your predicted model is saying it's a positive class, right? Your prediction is saying it's a positive class. Now verify from actual data. Is it positive? Yes, it is positive. Your model is saying positive, and actually it is positive. Both are intersecting, right, everyone? Can you observe? Right?
Yes,
Prediction
sir.
is saying positive, and it is actual positive. This will be known as true positive. This will be known as true positive because your actual is positive and model is also predicting positive. It's a true positive, right? So actually, whatever we say true positive, true negative, that is in respect of what is a prediction by machine learning model, right? So now we come here. Again, why model is saying what? Positive. But is it positive? Check from the actual. What it is saying? Negative,
Negative.
right? So this will be what? Not real positive. This is false positive. Here, it will be known as false positive. Means model, whatever by prediction is saying, it's positive, it's false, it's not true. So we'll call it as false positive, right? Similarly, come here to the negative. Okay, your model is predicting what? Negative. Your model is predicting what? And your actual is what? If you go over at the top, what is that? Positive. So is it a correct negative prediction? No, it's a false negative prediction. So what will you say? It's a false negative. It's a false negative. Now come here. Again, your model is saying it should be negative. But true is also what? Negative. So this prediction is correct. This negative prediction is correct. This is what? True negative. So now is it clear what is true positive, false negative, and true negative? And these are your correct results. These diagonal results are always your correct result. True positive, true negative means simple. When I am saying true positive or I am saying true negative, it simply means that these results are matching with my correct results or actual results. Results matching with your actual results. These are actual results, right? Whenever it is coming false positive or false negative, that means what? The prediction is not matching with
Actual value,
result.
actual results.
Clear? Now tell me, is it any doubt in confusion matrix? What it is?
Yes, sir. This part clear.
Mm-hmm.
But when we used it in Jupyter Notebook, when we
It came
run the code,
somehow it came like this.
yes,
Okay, it
we were
for
getting something
so
98,
9 9
11,
8
and
981 suppose 453. Okay, so always understand these are your diagonal are always what? This diagonal is always your true results.
true results.
All right, whatever you are getting here, suppose 47, 32. Among these, one of these will be your false positive, one of these will be false negative. These are your true results. Getting the point? These are your true result.
What is
Rest,
981 actually?
what this
Like
one?
what?
Oh, yeah,
Yeah,
yeah.
what is
See, directly,
981?
is not visible. So what you can do, remember, we have a formula for precision. How can I achieve that? Okay, let me tell you that. This way you can easily achieve that. Suppose, come here, what is your accuracy? If you talk about accuracy, from this you can derive what is my actual value. Suppose I come to the accuracy. What accuracy means? Accuracy means your correct predictions. What are your correct predictions? These one. So what is those? True positive plus true
True
negative.
positive plus true negative.
right? Upon total input that you pass, that true positive plus true negative plus false positive plus false negative. Clear? First of all, tell me, is it fine?
Yes, sir.
Right? So you will verify automatically one thing, what? If from confusion matrix, even you want to derive your accuracy, you can derive what? These 2 points will become your numerator. Okay. And again, these 2 points will come here, and rest of these 2 points, will become what? Your this result. Okay. This is one done. One way you can obtain. Next formula. Come to the formula. From the formulas, you will automatically get your answer. What you did, you compute your precision. There is another thing known as precision. What was the precision formula? Precision formula was true positive upon true positive plus false positive. Right? It was given to you. True positive upon true positive plus false positive. Okay. So what precision tells you? Understand? Precision tells you, and simple as that, out of the total positive predictions, okay, actually how many are true positive predictions? How many are actual true positive predictions? Clear what I'm saying? Your model
Yes, sir.
predicted something positive, out of which how many are true positive? How many are true positive, which is available in front of you, right? Similarly, what was recall? Recall was that true positive upon true positive plus false negative, right? True positive plus false negative, right? So what it is, understand, out of, suppose there is a class available, which has 100, suppose let me take somebody went for the COVID test. I give same example, okay? And in COVID test, actually 300 patients were COVID positive. 300 patients were COVID positive. But your model predicted what? See, out of these 300, 200 are COVID positive. Out of these 300, 200, actually the patients which came, which were 300, and all these 300 were supposed COVID positive. But your machine learning model says only out of these, 200 are COVID positive, right? So 100% these are coming from this only positive. So these are true positive, no doubt with that. But what happened? Rest 100, it didn't predict it positive. Actually, they were positive, but it predicted what? COVID negative. So these are what? Your false negative. These are what? Your false negative, right? So these are your false negative. So what it will become? True positive is your 200, okay? And false positive your 100. So actual result becomes what? 200 upon 200 plus 100. So 200 is what? Your true positive. Okay. From your positive class only, your model predicted 200. Okay. And what is your 100? Actually, they were positive, but your model predicted them as what? Negative. Your model predicted them as what? Negative. So when they are predicted them as a negative, but actually they were positive. So what we will, which kind of category it is? It is or false negative. Clear everyone? What is this? It is your false negative. Please tell me, is it okay? What I'm saying here?
Yes, sir. That is okay.
Okay. So you understand what is the purpose of precision? First of all.
Yes, sir. I understand that.
Mm-hmm.
Uh, the question that I had in my mind is like in current data set that we used, we are
Mm-hmm.
having only two values like 0 and
Uh-huh.
1.
Yes,
So
yes,
if
yes.
we had more than those values, then will my this matrix will be like 3 by 3
Yeah, it will increase, of course. It will increase as
confusion
per the class.
matrix?
It will increase as per your class.
So
It
it
will
will be
increase
3
as
by
per your
3
class.
then.
Yes, yes, yes. It will increase as per your class. The moment class will increase, accordingly you will decide. Accordingly, it will
Okay.
increase. Accordingly, it
Like
will change. Yeah.
for an example, we are having in output values low, high, and normal, or
Mm-hmm.
mild, mild, normal, and cold.
I'll do
Anything
one.
like that.
I'll do one thing, Hardik. I'll bring a data set for the 3 class and I'll show you practically. I think that will be better.
Yes, sir. That would be actually better
That will be better.
because
Yeah. That way,
I was
understanding will
getting
be
too
very.
much confusing
Got it.
with
Got it.
precision with 3 by 3
Don't
because
worry. Don't worry. The process will remain same always. Process will remain same. I'll tell you. I'll tell you with the 3 by 3. Is it fine?
Yes, sir, that is fine.
I'll take that one data set with having at least, I will take not more than that, because if I take 5 to 6 classes, then it will become very much complex to understand. I will take anything with the 3 or 4 classes, so that you can understand and analyze the data better, right? That will be better, I guess, right?
Right, sir.
So I'll do one thing. Uh, Today or tomorrow I'll fetch a data, and whenever our next class will be, I'll discuss that in one of the algorithm. Whatever algorithm we will study in that time, we will discuss that. Is it fine?
Yes, sir, fine.
Okay, okay. So let now move ahead. Okay, fine. Now see everyone. So now we are moving to one of the very, very important algorithm known as your linear regression algorithm. Okay, very, very, very common algorithm, very, very old, and at the same time, very, very uh, famous algorithm. Okay, what is the purpose? Here, regression problem it is. Okay, regression means what kind of output it can get. It will have output of the continuous type. Example, in which kind of problem we can use? For example, we have a house area. Okay, we have a house area and we have a corresponding price. And somebody says that if a house area is 50, the price is 50.2 lakhs. If a house area is 100, price is 70.2 lakhs. If it is 120, the house is price is 80.2 lakhs. If it is 100, it is suppose 90.7 lakhs, something like this. Okay, where output is your continuous numeric output, continuous variable. Okay, such problems are known as your regression problem. Example, it may be your stock price, right? We discussed stock price keep on fluctuating. So today, Apple price may be 45.23. Tomorrow, it can be 47.48, or it can be 40.23. Similarly, your petrol price, if we talk about petrol price, can be today 93.23. Tomorrow, it can be 94.56. Okay, day after tomorrow, it can be 95.75, something like this. Right? It can be something like this. So these kind of problem where output is a continuous numeric output. These are what your regression problems. Okay, so linear regression is basically used for which? Your, remember, regression problems only, not for classifications. Only and only for regression problems. Remember, we studied naive Bayes. Naive Bayes for only for classification. Linear regression is only for regression. Only and only for regression, right? But if you want to go with the classification, okay, a little derived from, we will move, we'll see that we will move from linear regression to another algorithm known as logistic regression algorithm. We'll see that second after linear regression, we'll see linear logistic regression only. Although name is regression, remember, but actually this logistic regression is a classification problem. Sorry, classification algorithm. Okay, so don't get confused by the name. Okay, regression is given, so it will be a regression algorithm. No, it's a classification algorithm. Okay, so let's study first of all linear regression. If you understand linear regression, logistic regression will automatically be clear. Okay, because we will make some changes in the same and you will understand that. Okay, so what is the purpose of linear regression? Suppose, understand everyone. Suppose I have a input variable x. Okay, and I have an output variable y. And for corresponding value of x, you are getting some y's like this, like this, like this, like this, like this, like this. Suppose this kind of data points are given to you. Okay, so where linear regression is helpful, understand when the relationship between your output variable and the input variable is what? Linear. The name is what? The relationship is linear. When the relationship is linear, your linear regression is very, very good algorithm. When the relationship between your output variable and input variable is a linear type, in that case, it's actually linear regression works very well. Very well. But if the relationship is non-linear, in that case, actually, it doesn't perform that well. In that case, remember, we discussed the algorithm decision tree regressor. I told you that time. In that case, your decision tree regressor is very good. But if your relationship is linear, linear regression works very well. And what is the objective of linear regression? Understand? The objective of the linear regression is to find the best fit line. The objective of linear regression is to find the best fit line which describe the relationship between input variable and output variable. Suppose this is my input variable, this is my output variable. So your objective is to find a best fit line which describes the relationship between these two variables. Okay, your objective is to find the best fit line which describe the relationship between your input and output variables. This is my objective is. Okay, so best fit line. But how will you find? What do you mean by best fit line? Option immediately comes. What do you mean? Why you are talking about the best fit line? What is the definition of best fit line? How can we say this is a best fit line or it is not a best fit line? Okay, so how we assume that? See, if we see this equation is what? This line I'm plotting here is a straight line. Okay, fine. Your actual points are these, which we are seeing here. This is your actual point. This is your actual point. This is your actual point. But this is the best fit line, which is my model has predicted. Okay, but equation of line is what? Y is equal to mx plus c. Okay, what I can say it is nothing but theta 1x plus theta naught. Any way representation you can do that. Where your c or theta naught is your intercept, and your theta 1 is your slope. Right. So what do you mean by a best fit line? I'll come to in that minute. But how can you see that? See, if you change the value of theta 1 and theta naught, okay, of course, or m and c, your line will change. Okay, whatever line is coming, your line will change, and according to that you will decide your line is a best fit line or not best fit line. So now let's come, what do you mean by best fit line? Suppose my model predicted this line. Okay, this is the line which is describing the relationship. So what we will do, we'll find out the distance between, I repeat distance, I'm repeating again distance. This is the distance based algorithm, remember. Okay, I will compute the distance between my original point, okay, my original point and the line. This means what? What do you mean by why I'm doing this? Suppose, as per my machine learning model, if I give you the value of x at this point and ask you, please tell me what will be the value of y. So what you will do, you will project this point onto this line and you will say, this should be the actual value. Okay, this should be the value. Similarly, at this point of x, if I ask you, my machine learning model will say, project it on the line. So this is your actual value. Okay, if I come at this point and ask, so it will say, as per my machine learning model, this should be this point. Something like this. Okay, but these predictions that I'm getting on this line are not actual, not correct. Your actual points are these points that you are seeing right now, these points which you are witnessing right now. These are your actual points. But as per my machine learning model, it predicted that this line will be your line which is having the best fit line. Okay, so normally what is the purpose of the best fit line? Let me come again. Just come on. Yeah, go on. Okay, suppose you find a best fit line on the basis of these data points. Sometime now you give you new value of x. So you will say, okay, this is the new value of x. Tell me what is the corresponding y will be. So you will project it on the line. So this is touching here. Now you will come here and tell this value of the y is the predicted value. This should be the actual value. This is how this line it is searching for. So that next time and I give you any x, you can tell what will be the corresponding y. Suppose I give you this x. Okay, so you will project it on this line. Wherever it will intersect, corresponding y value will be checked. And you will say, okay, for this value of x, the y should be this. This is why we are trying to find this line so that we can make the predictions. Okay, so objective is to find this best fit line, okay, by help of which we can make predictions. You give me any value of x, I will tell you what should be the corresponding value of y. For example, this x represents your area, okay, like this, and it represents your house price. So if I give you area, you should be telling me what will be the price. If I'm able to find that line, I will project this line onto, project this point into the line, and whatever is the corresponding y value, I will say this is the predicted value. So this should be your corresponding price. Right? So what is the ideal line? The ideal line is that a line which is closer to these data points, as closer to these data points as much as possible. Right? So that when I do the predictions, my predictions are correct. Okay. So how will I find these lines is closer to that or not? Let me come again. Come on, go. Come on, go. Yeah, like this. Suppose what I will do, this is my actual point, right? I will find distance of this point with this line. Okay. Suppose my point is, let's say, move out. My this point is corresponding, the value corresponding to this point is y1. So I said y1, actual value is y1. And the predicted value as per this should be suppose y1 hat. So I mentioned y1 minus y1 hat. Okay. And do the square of this like this. Plus, what is my second point? Second point is this. I will find the distance between this point and this point. Okay, this point and this point. So suppose this point is actually y2. And the corresponding prediction what y is giving me, that is y2 hat. square plus come to this point. Again, I will find the distance of this point with this point. So suppose my actual value is y3. Okay, and predicted value is y3 hat. So square this. Move ahead again. We have fourth point to find out distance between this point and this point. Y4 minus y4 hat square and so on. Right. So this is what you are seeing right now is known as sum of squared error, SSE. Okay, sum of squared error that we are seeing right now. Okay, but what we calculate actually, we find out mean squared error. We find out mean squared error. So how will I find out the mean square error? I will divide this error by number of data points. How many data points are there? Example 1, 2, 3, 4. Example, we have taken 4 now. 1, 2, 3, 4. So you can divide it by 4. And this becomes your mean square error. This becomes your mean square error. Now, what is your objective? Understand, everyone? Or even I can write this expression this way as well. See, I can further simplify this expression. This mean square error, I can call it as like this. 1 upon how many data points are there? Example, n. So I mention here n. Okay. Then I mention summation because it is a sum sign in between. I is equal to 1 to n. Perfect. What is the first point? Y1 minus y hat. So instead of 1, I will mention yi minus, what is this? Y1 hat. I mention yi hat whole square. Right? So can you tell me, everyone, can I write the above expression in this manner or not? Please tell me.
Yes, sir.
Right? Same expression I want to write. Okay, same expression I want to write. Okay, so what is my objective? My objective is actually to find that line. Okay, that line which gives me minimum MSE, minimum mean square error, minimum mean square error. And how will I find out actually? How will I decide which will happen actually? What is my formula? My formula is this one: y is equal to theta 1x plus theta naught, or mx plus c. So when I change the value of c and m, I will get a totally different line. Suppose I mention c is equal to 1. So where c is what? Intercept. So my line will start from 1. Okay. Then I mention suppose some x. So suppose I get this line. Right. Again, I change value of c to 2b2. Okay. And suppose I made m is equal to 0. I made c is equal to 2 and m is equal to 0. So what I will get? I will get a constant line like this 2. Right. I made suppose m to be minus 1. Okay. And c to be 3. So what equation will become? Y is equal to minus x plus 3. So your line will start from where? 3. And what is the intercept? Oh, sorry, what is your slope? Slope is negative. So you'll get this kind of line. So we see that whenever we will change this theta 1 and theta naught, we will get a different line. Agree or not, everyone? Tell me.
Agreed.
Right? So whenever we are at a different line, so every line's distance with this line will be different. Some lines will be very far away from these points, so they will give you a different value of MSE. The sum line will give you a different line of value of MSE, because what we will do, we will find out the distance of these lines, whatever line, suppose this line is, so we will find out distance of this point with this point, this point with this point line, this point line with this point with this line, this point with this line, this point with this line. So it will give me an MSE, example, MSE1. If this line, so we'll compute the distance, again, same process, this point with this distance, this point with this line, again, this point with this line, this point with this line, this point with this line, this point with this line. So we'll give a different MSE this time, right? So if we change the value of theta 1 and theta naught, I will get a different line, and the distance of these points, your actual point from these lines will be different. So we'll get different MSE all the time. So there can be certain one MSE which will have minimum MSE, right or wrong, everyone? Certainly there will be a line which will have the minimum MSE, means which is closest to your points, which is giving you minimum distance from your actual points. That line you have to find out. Okay, so what is my objective? My objective is to find out those value of theta 1 and theta naught. This is the problem statement now. I have to find out those value of theta naught and theta 1. Okay, that is your best fit line you're talking about now. So line parameter depends on what? Theta 1 and theta naught, or M on C. So my objective is to find those value of theta 1 and theta naught which give you minimum what? MSE. And the line which is giving you minimum MSE will be known as your best fit line. Clear, everyone? Please see and tell me.
Yes, sir. Clear.
Yeah. Okay. But actually, what we do instead of using directly MSE, we make an objective function of the same. Okay. We same thing MSE. We can say this is our objective. Our objective is to what? Minimize of MSE. Okay. But if we see the official documentation, we call them as instead of MSE. Although it is MSE only, they're represented by J, known as cost function J, which is a function of what? Theta naught and theta 1 equals to this. J means a cost function equals to 1 by n, summation I is equal to 1 to n. It is nothing but equivalent to your MSE only. Right? So objective is what? Minimize this cost function or minimize the MSE. Give me that value of theta 1 and theta naught, which give you minimum cost function or minimum MSE. But for simplification purpose, if you see several books, they will introduce here one more term, 2. They will introduce here one more term instead of this, and they place a 2n. You may be thinking, sir, why? Just for mathematical simplification. That's the only reason is because ultimately we'll see that when we will minimize this j function, actually we have to find out a derivative of this, what you are seeing right now. Okay, we will have to find out the derivative of this. So we know that if somebody is having two examples, 2i or something, if there is x square, if I find the derivative of this with respect to x, so what I will get? I will get 2x, right, everyone? And this 2 and 2 will be cancel out each other. So ultimately, because we know that we have to find the derivative of this 2 will come ahead, and to cancel that 2, they actually introduce 2 here. So this equation becomes actually 1 by 2n, not 2 to the power n. Remember, everyone, 1 by, let me just use an eraser. Come back. Equation actually becomes 1 by 2n. If you don't even use it, fine. Just your mathematical expression will increase. That is the only purposes. Okay. So what is this? This 2 is just used for simplification purpose. So what is my objective in linear regression? Remember, to find out the value of weights or theta 1 and theta naught, which minimizes my MSE or which gives me minimum MSE, or we can see which gives me best fit line. Clear, everyone?
Yes, sir. But one thing I wanted to ask.
Mm-hmm.
What if we will have multiple inputs?
I'll
So
come to
can we
that.
apply linear?
I'll come to that. Yes, we can apply. We can apply. Just wait. That is known as multiple linear regression. I'll come to that. I'll come to that. Okay. And first understand with the help of one, automatically will understand for the multiple cases. Okay. So let me move ahead now. It is clear. Okay. Let me come here and just hide it. See. Now suppose this is my J. Okay. Whatever J is. And suppose what is happening right now, it is given to me. Your actual training data is like this, X and Y. Okay. X is 1, suppose Y is 1, X is 2, let's say Y is 2, X is 3, let's say Y is 3, X is 4, let's say Y is 4. I'm just taking 4 points for now. Okay. And your model initially says that for simplification purpose, I'm telling you because you will they understand what will be the shape of cost function. Very commonly asked question in the interviews, what should be the shape of cost function in case of linear regression? Okay. They ask you a question. Okay. So equation, we assume that this one, Y is equal to theta naught plus theta 1x. Okay. So let's pick one value. Let's say theta naught is equal to 0. So I'm picking y is equal to theta 1x. Okay. I assume theta naught is equal to 0. So y is equal to theta 1x. Okay. So let me do one thing. Let me pick 3 values of theta 1. 1 theta 1. Let me pick. Suppose it start with theta 1 is equal to, let's say, 1. Okay. Theta 1 is equal to 1. I pick my value. Theta 1 is equal to 1. This is my prediction. Suppose y hat. Okay. Theta 1x. This is my, the equation predicted by machine learning model, where it assumes that theta 1 is equal to 1. And I will plot my cost function here. Here I will mention theta 1. Here I will mention j. And just remember the equation. What was the equation? Equation was 1 by 2n summation I is equal to 1 to n yi minus yi hat whole square. Right? Just remember this equation. So let me come here. So I assume theta 1. When I assume theta 1, what this y hat will give me? Y hat will give me x only. Y hat will give me, if I put 1 here, what I will get? X. So when it is x, what my y hat will become, everyone? My y hat will become y hat is equal to x. Same x as is the x, right? Tell me, is it fine? I use theta 1 is equal to 1. When I put theta is equal to 1, what is my equation becomes? Y hat is equal to x. Is whatever x is, that will become my predicted value. So I put x value 1, 2, 3, 4. Right? If this is the case, understand everyone, if this is the case, what will be the difference between y minus y hat? Can we compute? 1 minus 1 will be 0, 2 minus 2 will be 0, 3 minus 3 will be 0, 4 minus 4 will be 0. So if we compute this, what we will get? Error to be 0. Right or wrong? Please tell me.
Right, sir.
Right? This is the ideal case. Okay. So suppose I mention here, this is my theta 1, 1. Here I will get the minimum value 0. Fine. No issue. Now let me check another value of theta. Come here. Let's check. Suppose theta 1 this time to be 0.5 or yes, whatever it is, 0.5 or minus 0.5, whatever you want to pick. Suppose I put 0.5 this time. Okay, I just put 0.5. So when I put 0.5, what will equation will become everyone this time? It will become 0.5 times of x, right? Clear everyone? Because I put theta 1 is equal to 0.5. So what equation I get? 0.5 times x. So if I find out my y hat this time, what will be my y hat? 0.5 times of x. What will it become? 0.5. It will become 1. It will become 1.5. It will become 2. Right or wrong? Please tell me.
Right, sir.
Right. Now let me do one thing. Let me find out this. Y minus y hat for the same. What it will be? Y minus y hat. What will be y minus y hat? This is my actual y. This is my y hat, predicted value. So 1 minus 0.5 will be 0.5, right? 2 minus 1 will be 1. 3 minus 1.5 will be 1.5. 4 minus 2 will be 2. Okay. But here what we need a square of these. So let me do the square of these. So what will be y minus y hat square? It will be 0.25. It will be 1. It will be 2.25 and it will be 4, right? Everyone? Tell me, right?
Yes, sir.
So to find this cost function, what we will need, how many points we have taken? 1, 2, 3, 4. So it will become 1 upon 2 into 4 and sum of these values, right? What are these values? 0.25 plus 1 plus 2.25 plus 4. Okay. If we compute this, what will become? 6.25 plus 7.25 upon, sorry, 6.25 plus 1 is 7.25 plus 0.25 is 7.5. So actually I get the value to be 7.5 upon 8, right, everyone? So we can compute this value. What is the value? Quickly calculate if you have a calculator, or we can do rough approximation as well. It will be around 0.935 something, 0.937. Okay, 0.937. So suppose, let me mention here, this is suppose one value. Okay, or here it is a one value. So 0.9 will be somehow down here, 0.9 something, but it is what? 0.5. What value we have taken of the theta 1? 0.5. So 0.5 will be somewhere here, right? So my new value will be, put something here. Okay, new value of cost function will be something here if this is j is equal to 1. This was your value when theta 1 was 1. This is your value when it is 0.5. Similarly, now let me pick one more values. You will understand it easily, right? Now I'm taking theta 1. Earlier we took 1, then we took 0.5. Now let me make it 1.5. Okay, let me make it 1.5. When I make it 1.5, what value I will get, everyone? 1.5 times of x. What will be 1.5 times value of x? It will be 1 y hat 1.5, right, everyone? This will be 3. This will be 4.5 and this will be 6. Tell me, everyone, clear or not?
Yes, sir.
Right. Now what we will find out? We will again find out what? Y minus y hat, actual value minus predicted value. Find out what is y. Y this. Y minus y hat is 0.5 minus 0.5. Fine. Y minus y hat 1. Y minus y hat again minus 1.5. Y minus y hat minus 2. Right, everyone? Clear so far? Please tell me.
Yes, sir.
Right now what we can do, we have to find a square of this. Okay, because y minus y hat square is needed. So find out the square of this. Y minus y hat square, 0.25 plus 1, 2.25, and it is what? 4. Clear? And if you see this result and this result is exactly same. See,
Yes.
right? That means this error will also came same 0.9 something, 0.937, something like this, right? But it is what value of theta? This is that the value of theta 1 is equal to 1.5. So 1.5 will be where? Somewhere here. And value will be what? Somewhere here. If you can see, actually your shape will be, when you put multiple values, you will see that your shape will be a convex shape, very much like this, right? Sorry, I missed the point, but you understand the point, right? It will be very much like this, a convex shape. So very common ask a question asked in the interviews as well. Okay, what is the shape of your cost function in case of linear regression? Okay, so the answer is convex. Okay, convex. So what we have to find? We have to pick the value of theta 1 example, which should give you what? Minimum cost function. In this case, it is 1. But actually, when your machine learning model will start, so it will pick the value randomly. Understand? It will pick the value randomly. Never know which is the minimum value, right? So it may pick any value. It may pick any value. Suppose it picked theta 1 to be this at this point. Okay. At this point, what will be the cost function? You are here, which is very high cost, right? Which is very, very high cost right now, what you are witnessing. Clear everyone what I'm saying, right? So initially it will pick randomly. So randomly it picked theta 1 is equal to this. You land up here. Now understand everyone, for optimization purpose, what will come into the picture? A very, very important algorithm known as gradient descent algorithm is going to the picture. Gradient descent algorithm. Okay, what it says, understand. It says that I will update the weight. How I will update the weight? Suppose my new weight will be theta 1. Theta 1 new will be theta 1 old minus eta times. Eta, I'll tell you what is the eta. Del j means derivative of this one with respect to the weight that you are using, that is theta 1. This, according to this, you will update your weight. Now you see, sir, how this equation will work. See everyone, what it does. Okay, suppose initially your machine learning model predicts the value of theta 1 to be this, due to which you get this cost. Fine. Okay, so what gradient algorithm says, compute the del j by del theta 1 at this particular point. Whatever is the theta value there, compute the slope. What is the derivative? Derivative is nothing but slope. So compute the slope at this particular point. Okay, so this curve is going upwards, everyone. So at this point, your del j by del theta 1 will be what value? It will be a positive value, right or wrong? Tell me, everyone. Because this curve is going in which direction? Upward
Upwards
direction. So
direction.
slope is what? Positive, right? So if we put that positive value here, okay, so this is your old theta. Understand, this is your old theta. Okay, when you subtract from this something positive, what you will get? The value which is less than the earlier value, and this is your objective. When it is very high, come towards the minimum point, reduce the value of theta, reduce the value of theta to come to the point at minimum point. Automatically it will happen. You don't have to do it manually. Automatically it is going to happen, because at this point your slope will be calculated, and as the slope is positive at this point, you will get some positive value. And because the equation is what? Theta old minus theta time, this term will always be positive. Remember, this will always be positive. Okay, learning rate means, you, what I'm saying, decrease your theta, but how much we want to decrease the theta? But by how much you want to decrease the theta means how much value you want to put that. Okay, so you are decreasing the theta, fine. That's why I'm subtracting. But what, why, by what ratio I want to decrease? That is nothing but your learning rate. Okay, so you have to put it very smartly. Don't put it too much high. Means it should not happen. You are here, okay, and you decrease the value of theta 1 in a such a manner that it come here. If you decrease, you put the value of eta to be such that your theta 1 decreased, okay, decrease, fine, accept it, decrease, but decrease so much that you land up here, where again you are having a very high error. Okay, so don't pick the value of eta to be very high, not to be very small. If it is very small, it will decrease by a very small amount. It may come from here to, it may come from here to here, right? Again, it may come from here to here, something like this, right? So what will happen if we are putting very small value? Okay, we'll come to the minimum point very much later. because it's an iterative algorithm. It will happen in multiple steps, not in one go. It will happen directly. It will happen in multiple steps, again and again, again and again. Again and again, your weights will be updated or theta will be updated. Okay. So if I pick a small value of eta, my small theta will be changed by a small value. But if you put a larger value of theta, it may change to a value that it is again going to give you a very high error. So you have to pick smartly value of theta. So what happened here? Your del j by del theta will be positive. Okay. So I put a positive value here. Theta is always positive. So of course I can say my new theta will be less than my old theta, right? Everyone or not? Please tell me first this. My new
Yes.
theta will be right. So that means we are traveling in right direction or not. You will travel towards this minimum point. Clear? Similarly, suppose you pick the very small value of theta like this initially. Randomly we are picking, we never know. Suppose I come up here, okay, and I pick the value of this. At this point, what is your cost function here? This is your cost function. Again, very high. So what you will do? Same algorithm will work. Now you will again compute the slope here. Okay. Suppose the machine learning model at the beginning phase predicted theta such that which is landing you here. This is your theta one, which is taking you here. So at this point, you will compute the slope. Okay, and this slope is where going in the downward direction. So what will be your del j by del theta one, everyone? This term it will be negative because slope is what? Negative. So if you put a negative value here, del j by del theta, everyone, this time sign will become what? This is negative coming. Then what will happen? Negative and negative
Positive.
will become
It will
what?
become
Positive.
positive.
Yeah. So what theta one will become? More than old or less than old?
It will increase. It will more.
Yes.
It will be more.
Yes. Yes. It will be more than the old. That means your theta one will be instead of this, you will move in this direction. That means you are moving in the right direction. Automatically it is going to happen. So whatever you are witnessing, this is nothing but known as what? Remember? Gradient descent. What you are witnessing right now. Okay. And this is your update equation. How it get updated. It doesn't happen in one go. You have to do then multiple iterations. In multiple iterations, it happens. Not in one go. Tell me everyone clear. What is the, first of all, what is, how do we achieve to our cost function? First thing, okay. What is the shape of our cost function? How gradient descent is helping us in to move to the minimum error point? Okay. And remember, gradient descent is what? It's not a machine learning algorithm. Your gradient descent algorithm is your optimization algorithm. If you tell someone I know machine learning or yes, even machine learning, they'll ask you, do you know what is the gradient descent? Now at least you can answer everyone. Tell me so far, is it fine?
Yes, sir.
Okay, now let me move ahead. Okay, let me move ahead. Come here, hide it. Okay, so actually there are three variants of gradient descent. Understand everyone? Three variants of gradient descent. Even more are there, but three are very popular. I say popular gradient descent algorithms. Okay, people are researching and producing further, but three are very popular. One is known as your vanilla gradient descent. Vanilla gradient descent, or sometimes it's called it as batch gradient descent. Okay, vanilla means original flavor. So initially somebody launched, then which was the algorithm available? Only this algorithm, batch gradient descent. Vanilla means raw flavor, raw, right? Without any flavor. Okay, vanilla batch gradient descent. Okay, second one is stochastic gradient descent. Stochastic gradient descent. Okay, and third one is your mini batch gradient descent. Mini batch gradient descent. See, what is the difference between these three? How they perform? Okay, ultimately everyone has to update your weight, right? Theta one is equal, theta one new is equal to theta one old, okay, minus eta times del j by del theta one. Okay, this is ultimate purposes. But how frequent this weight update will happen on the basis of that difference is there. How frequent this weight update will happen? Okay, so suppose you have a data set available in which X is the input, Y is the output. Okay, we have one data point, 1, 2, 3, 4, 5, 9, 10, 15. Okay, suppose we have some points available. In batch gradient descent, understand, your weight update will happen when all your data points are considered. After that, weight update will happen. Okay, so one iteration will be known as what? In one iteration, you will cover all the data points. When all data points have been taken into the consideration, all data points you have traversed, right? After that, your what happened? Your weight update will happen. Okay, so again, you will, when all the data points have been covered, only then you will update the weight. That's why the batch is there. Complete batch will take into the consideration. Only after that, your weight update will happen. Okay, but in what happened in this process, actually, this becomes very much slow. I'm giving some for example. So sometime you may have 10,000 rows, right? 10,000 rows. Okay, in that case, what will happen? If you are traversing all 10,000 rows, it will take a lot of time, and then that 10,000 rows will be known as one iteration. So after one iteration, your weight will be updated. Okay, if it is not satisfactory, again you will traverse 10,000 rows. Again, further weight update will happen in the second iteration. Again, if not satisfactory, you will again go and cover 10,000 rows, and then weight update will happen. So in this case, when entire batch is covered, only then weight update happens. Okay, and it may happen, you may reach in your optimum point in multiple iteration, maybe 10, 50, 100, 200, 300 iterations. So it's a time taking process. Okay, to deal with that problem, what has been designed? Stochastic gradient descent has been designed. Stochastic means random, first of all. Stochastic is a random process. Remember, stochastic process is a random process. So what will happen in this case? Weight update will happen after each data point. Here we have to wait till all data points are covered. In this, no, it is not going to happen. You will pick any one random data point. Suppose this random data point. Okay, you compute your equation y hat. You find out the error, and immediately after that, what will happen? Your weight update will happen. So in stochastic gradient descent, weight update will happen after every data point. Okay, weight update will happen after every data point. That's why you're quickly able to reach to the optimum point. Here, weight update is happening after covering entire data points. Here, weight update will happen after every data point, after every data point, every data point. Here, after all data points. So which is having more frequent updates? Of course, stochastic. Which is having very less frequent updates. What is that? Vanilla gradient descent. Right? Here, weight update will happen after every data point. Here, weight update will happen when all the data points are covered. That is the basic difference. Again, but here again, what is happening in stochastic gradient descent? Weight update is happening very frequently, very frequently, very frequently, very frequently, right? So a compromise between them is there, known as mini batch gradient descent. What it does, your entire data set is divided into the batches. Suppose you have 10,000 rows in your entire data set. So we may create batch size you will specify. Okay, you may create mini batch gradient descent, which you will specify batch size. Suppose you specify in 10,000, create a batch of 1,000. Okay, so 10 batches you will get. Because 10,000 there, your batch size is 1,000, you decided. So how many batches will be there? One. So weight update will happen after every batch. These are known as mini batch actually. Your complete batch is your entire 10,000 rows, which is this. Okay, these are small batches made from the big larger batch. So these are known as mini batches. So after every mini batch, your weight update will happen. This is your mini batch gradient descent. Okay, so in your vanilla gradient descent, weight update will happen ever when entire batch is covered. Means all the rows of the data point are covered. Okay, but it takes a lot of time. So we devise what? Stochastic gradient descent, in which weight update will happen after every data point. But that is too frequent, so we made a compromise between them. Okay, we come with the idea of mini batch gradient descent. Okay, so we'll combine the properties of vanilla at the same time. Stochastic means stochastic was frequent updates. Vanilla means complete batch, means a batch they are taking into the consideration. So we took batch from vanilla, but not complete batch. Okay, we divided that complete batch into the mini batches. Suppose example 1,000 rows each. Okay, and frequent updates we derive from stochastic gradient descent, but not like that. In stochastic, after every data point, your weight was updated. Right now, it will not happen. Your weight will be updated, or your thetas will be updated after every mini batch, means after 1,000 rows, 1,000 data points have been covered, then your weight update will happen. Again, 1000 rows covered, weight update will happen. Again, 1000 rows update, weighted update happen. So here, 10,000 rows, weight update will happen after every 10,000 rows. Here, weight update will happen after every row. Here, weight update will happen after every 1000 row. Clear everyone, the three differences, please? Clear? So how frequent, how they have differentiated on the basis of how frequent your weight update happens. How often these equations get computed again and again. In vanilla, after entire data points are covered, this will be updated. Then wait for again 10,000 rows to be covered. Okay. Stochastic, one data point gone, update. Second data point gone, update. Third data point gone, update. In this, no. 1,000 rows gone, update. 1,000 rows gone, update. 1,000 rows gone, update. Okay. So it will have more frequent updates in comparison to batch, but less frequent update in comparison to stochastic gradient descent. Okay. Now, very interesting scenario is this. If we come here, okay. So we saw just a shape here, right? It was theta1 and it was your J. Okay. And we saw such kind of shape. Okay. But in practical scenario, your shape may not be ideally this. Okay. Your shape may be like this. J and theta example I'm plotting. It may be like this. This one, then 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 this one. It may be a shape in practical scenario, right? So understand these point, the point which is minimal, right? This one, the point which is having the minimum value, it is known as global minima. Global minima. Okay. And these point, okay, these point, this point, this point, this point, this point are known as local minima. Okay, remember the point, the value of J, which is minimal, okay, of everything, that is known as the global minima. And in between that, you are seeing these dips. Okay, these are known as local minima. Your machine learning model should not stuck here, but actually your batch gradient descent has a problem. Sometimes it stuck there because updates are very less. You stuck there. Okay, so if you want to get away from this, your objective should be to reach the global minimum. You want minimum value of the cost function. So your objective should be not to stuck in the local minima, but to reach where? Global minima. So how we can go from local minima to global minima? By using two approaches. Either use your stochastic gradient descent, because updates are frequent. So you can go from here to there, right? Stochastic or mini batch gradient descent you can use. Your batch gradient descent stucks there in the local minima. And properly choosing the value of learning rate, you can get out from your learning rate. Okay, even what people have done, people have devised further algorithms. Further, they are researching how to get out fast from the learning, these local minima. They have used momentum approach, in which quickly you can go from one location to another location. Means from here to there. For example, you are stuck here, quickly it will move here. Okay, so people are researching. Even it may be possible in future you may use further thing. Okay, and you will develop your own algorithm. Okay, which will be better than the already developed algorithm. But basically, are three RUs, as I told you, your batch gradient descent or vanilla, then your uh, stochastic gradient descent, and your mini batch gradient descent. Okay, your batch gradient descent or vanilla gradient descent has a probability or prone to stuck to the local minimum. But how can we avoid them? By using a stochastic gradient descent or mini batch gradient descent and properly choosing the learning rate. You can get out of this. Although there are people researching next stroke gradient descent, they have devised momentum-based approach. They have decided. Even they keep researching, keep researching is going on. So if you read the research papers, you will find out those values available here. Okay, so you may be possible you may develop your own algorithm, right? So now we saw that. Let me come here again. Okay, so far what we saw only. Let me come on. Yeah. So far what we saw, we just saw only this y is equal to x. But in actual, it may be theta x1, x2, x3, x4, like this. Okay, and this may be your y. So y may be function of x1, x2, x3, x4. Okay, and you have to find a best fit line to describe the relationship between these. Okay, to visualize it is very difficult, but understand what is the process. Process is same, exactly same. This case actually becomes your multiple linear regression. This case becomes your multiple linear regression. So what we do, we try to find out a best fit line. How? This y is equal to theta naught plus theta 1 x1 for first parameter plus theta 2 x2 for second parameter, for theta 3 x3 for third parameter, for theta 4 x4 for fourth parameter. Even you can extend them. Okay, still your problem statement remains same. Still your output remains same. Means this is your cost function. J is equal to just that. This time J will become a function of theta naught, theta 1, theta 2, theta 3, theta 4. Okay, whatever parameters are, function will be same 1 upon 2. If we have n data points, then n summation I is equal to 1 to n yi minus yi hat whole square. Still objective function will be same. But what now? When the update will happen, how many weights you have to update, everyone? 1, 2, 3, 4, 5 weights you have to update simultaneously. Earlier we saw only one equation was getting updated, but it is multiple linear regression. Then multiple weights will be updated at the same time. How? We'll mention this theta naught new will be nothing but theta naught old minus eta del j by del theta naught old. Example, right? Theta 1 new is equal to theta 1 old, okay, minus eta times del j by del theta 1. Okay. Similarly, theta 1 2, sorry, theta 2 new is equal to theta 2 old minus eta times del j by del theta 2, right? Similarly, theta 3n, n means new, is equal to theta 3 old minus del j by del theta 3. Okay, so these update will happen at the same time. At the same time, you have to update these weight equations. Okay, everything remains same. Everything remains same. Just that same your objective function is the same. Just that now j has become, instead of function of only one parameter, it will become a function of theta naught, theta 1, theta 2, theta 3, theta 4. Okay, it will become function of multiple things: theta naught, theta 1, theta 2, theta 3, theta 4. Right, and you have to update your weights. All the weights have to be updated. This one, this one, this one, this one, this one, using same equation. Using same equation. Does that you will update theta 1 as per this equation, theta 1 using this equation, theta 2 using this equation, theta 3 using this equation. But these updates should be simultaneous update. Okay, there should be simultaneous update. Don't worry, you don't have to do it manually, anything. Everything of these will be done automatically by your linear regression algorithm when we will import it. Automatically it is going to happen. You don't have to worry about it. How I will do this manually. But I'm telling you, for the interview purpose, actually they ask you this. If you give the interview somewhere, they will ask. You don't have to type even a single thing. You don't have to worry about these things at all. You have to just set few parameters like learning rate. What should be my learning rate? And this learning rate can be hyper parameter. Like remember, there was you put example k. For k nearest neighbor, we put k. K will be 1 or 3 or 5 or 7 or 9. Similarly, yesterday we saw a max depth parameter. Okay, so that max depth parameter is a hyperparameter. We set 2, 3, 4, 5, 6. Similarly, you can set your different hyperparameters, lift and learning rate, and you can check your result for which you are getting your result properly. Okay, now let's come to one more challenging. Right now, we have taken only theta 1 to be x directly proportional, theta 1 x1, theta 2 x2, theta 3 x3. Let's take one more challenging scenario. One more challenging scenario, this one. Okay, and suppose this is what, let's say this is my x, this is my y. Okay, and suppose some data point for corresponding value of x, which is the y. Again, this is the y, this is the y, this is the y, this is the y. Tell me, everyone, is there any line which can describe the relationship between them? Any straight line?
No.
Right? We cannot do that. In such cases, actually, what you go for? Polynomial linear regression. Polynomial linear regression. Immediately should come to your mind. How? Okay, see. So far, what we wrote the equation, y is equal to theta naught plus theta 1x. Fine, perfect. But now let us introduce the higher degree polynomials as well. Okay, let me introduce one more polynomial of x. Let's say theta 2 x square. Okay, when my requirement is not able to achieve by using simple linear relationship, then what we introduce? We introduce polynomials of higher degrees. Okay, so I introduce a polynomial of degree 2, for example, x square. That we will do. When we implement this, you will see that we will do the same implementation. Okay. So that's why your visualization becomes very important, right? That's what I told you. If you are mastered in visualization, see the relationship between input and output, you will get some idea at least, okay, what kind of relationship we are having between my input and output. Of course, when it will be actually multiple inputs available, at that time it will be very much difficult for you to analyze. But if you take some time, spend some time, then you will understand it. Okay, yes, we can do that. But multiple taking at the same, because visualizing the relationship in a 3D becomes very much difficult. Okay, so at least if data is simple, you can analyze. But what is the purpose of the polynomial regression? Okay, so you can experiment. Okay, let me put x is equal to 2, let me put x is equal to 3, let me put x is equal to fourth polynomial, let's see if my result improves. So this polynomial degree can be again a hyperparameter. Instead of directly choosing theta naught and theta 1x, I may choose, okay, let me try x square as well, let me pick x cube as well, and let's check how much error I am getting. Is it improved, is it improved, is it improved? This is a hyperparameter that you can choose on. Okay, if you see that if I pick this theta 2x square additionally, a polynomial term when I use, okay, and see everyone, if I select theta naught to be 0, example, theta 1 also to be 0, and theta 2 to be 1. Okay, I choose these values, theta naught to be 1, theta 1 to be 0, theta 2 to be 1. Then what equation I will get? Y is equal to x square. Right, everyone? Tell me, correct or wrong?
Correct, sir.
Right. So what is the shape? Can you predict from this? This is a parabola. Right? This parabola. Correct? Tell me.
Yes, sir.
Right? Of the shape x square is equal to 4ay. So somehow, okay, somehow this can be, somehow, I'm not saying exact, but somehow this can predict this or not. Tell me, everyone. It is better than any straight line
Yes.
in predicting the relationship. This is how it comes into the picture. Okay, this is how it comes to the picture. So sometime your simple linear equation or linear regression will not be able to meet your requirement. Okay, if there may be complex relationship like this, example, this kind of, you have data points something like this, here, then here, then here, then here, then here, then here, and then here. Okay, in that shape, actually you should experiment. Actually coming here, and when we have multiple data points available, it's very much difficult for you to visualize. Okay, and actually only way available for you is experimentation. Play with it, because visualizing your 3D, even 4D, 5D data is very, very difficult. Up to 3 inputs, okay, you can see a 3D data. When it becomes 5 variables, 6 variables, 7 variables, it will be very much difficult for you. So only option available to for you is what? Experimentation. Let's put different degree polynomials and see if my result is improving or not. Start with a simple, okay, then improve. Then increase the polynomial degree, then increase the polynomial degree, then increase the polynomial degree. If whichever is giving you best result, take that polynomial degree. That will give you the best result. This is the only way we can do if we have multiple input variables available, right? So this is nothing but what your polynomial regression. Clear, everyone? So we have to introduce higher degree polynomials. Here we have used one parameter, so we have used that only those polynomial of degree 2. If we have multiple parameters, we have to introduce those as well. Clear? Please tell me.
Yes, sir.
Okay, so we'll continue on Monday, everyone, with the implementation of the same. Whatever we have studied today, we'll implement our polynomial regression, okay, and we will implement our linear regression as well with a proper example. Okay, fine, everyone. So can I end for the day? See you on Monday. Okay,
Yes, sir. Thank you, sir.
okay, everyone. Bye bye. Take care.
Yeah, bye, sir.
Bye.